Hi everyone, and welcome to the second RobotDynamics exercise. This week we'll learn about velocities, how to present them in different frames, and how to propagate velocities per link to a final velocity and the end effector. Let's first do a small recap of what we learned last time. So from the last exercise, you should have understood that we can represent the position vector from one point to another point. So let's say we have an inertial system I here. We have another and an origin point maybe called A or I itself, and another point P. How to represent this transformation from I to P. And what we've seen is that you can use homogeneous transforms in this notation, so GAB transforming a vector that goes from B to P into one that goes into A from P, like this. And this homogeneous transformation matrix is composed of a rotation matrix, CAB, a position vector, RAB in A, 0, 1, which is in 4 by 4. Furthermore, the any vector represented in A frame can be rotated from another frame, for example, B frame, like so. And it doesn't matter from where to where it is, but often let's just use for consistency here AP and AP, so it's clear that the vector itself does not change, only the representation. And finally, we've learned about composition. Which means how to chain together or how to concatenate multiple transforms. That is especially useful if we have a robot arm that comprises of many different links. So we have P1, P2, and maybe P3 as the end effector. So the composition works as follows. We have TAB is TAB prime, which is some intermediate point, TB prime B, and the same for rotation matrices. So CAB is CAB prime, CB prime B. And the last exercise, this is basically what you have used to propagate from individual transforms along single links, which were easy to set up because they usually just included a displacement in one direction along one coordinate axis, all the way to from the end effector to the base of the system. All right, so what we will do today is consider velocities. So compared to before, where we just described positions, we now want to describe the velocity or the rate of change of a position and orientation of our end effector, for example. Our notation will be as follows. So when we write VA, we denote the linear velocity of point A or rather capital A. And it usually needs a form of representation, so you can encode it. And that will be VA in, let's say, for example, B frame. Just as before with the position vector, we need to use a specific frame to express our vector in. And the same goes for angular velocities. So yet there we use omega. Omega A is the angular velocity of, you cannot really say point A because points by themselves don't have an orientation. So let's say of body A, which is typically the body that A is attached to, so the whole entire link. And on a quick aside, notation-wise, when we write VA or omega A, what we really mean is VIA or omega IA. So if you don't see double indices, what we mean is the absolute velocity linear angular, which means with respect to an inertial fixed frame, which we always call I in this lecture. So how do we define those velocities? So the velocity A is defined as the time derivative d by dt of the position vector from I to A. And that is basically exactly what it means. So how does the position vector change over time? The position vector to a point change over time, and this is defined as the velocity of this point. Unfortunately, there's no such a nice formula for rotations because we cannot represent a rotation in terms of a single, let's say like a position vector. There's no single rotation vector that works in the same way as here. So unfortunately, we have no similar formula for rotations. Now, this formula here in the box is nice to conceptualize what a velocity means, but it doesn't really help us to code it because here we have not yet introduced frames. And frames, remember, are what's needed to encode a vector in terms of, let's say, 3 tuples, your 3 coordinates. So the formula for this, if we want to represent the velocity of a point in a certain frame, then from above, this is RIA, and basically we want this entire thing to be expressed in B frame. Notice where I'm placing the B. It is outside of the entire derivative. So we've already taken derivative and then we express it in the B frame. This is important because it's not the same as directly taking derivative of the vector that is already represented in the B frame, as you will see here. This is the Euler formula that you might have seen from previous dynamics courses. So how this will resolve to, and you'll have derivations in the script of this, is that we have the time derivative of our position vector expressed in the B frame. So notice here, now the B is inside of the derivative. Let me take the parenthesis like this. Plus another term, which is related to the angular velocity of the frame that we are expressing the velocity in. So cross product RIA in B, which is at the end the same as directly transforming the time derivative of our RIA in I. Why is that? It's because if you expand this the expression on the right hand side here, so the d by dt r of IA in I, then you will see that the omega term, the second part, will disappear. That's why if you already have expressed the position vector in the I frame, you can directly take the time derivative. If you have it in a different frame that is potentially moving, like the B frame here, then another term appears, which is related to this, which includes this omega. And to make this a little clearer in terms of explanations, we have basically this first part here is the change of RIAB element-wise. This is what we would anyways intuitively do. And the second part is the contribution of the rotation of the reference frame. And it should become clear that if your original vector, if the frame B is actually identical to I, which means it doesn't rotate, then of course this term disappears. Okay, this is probably the most important formula that you will use throughout this exercise. What we will look at last is how do we use this formula when we have to transfer velocities across multiple frames, which means across an entire chain of the kinematic link of the robot. For this, let me go to another slide. So consider the following scenario. So we want to look at something across multiple frames. So, for example, we have the inertial frame here, X, Y, Z, which might coincide with the base of our robot. Then we have a point A somewhere out here, and the first link basically is this beam here. And we attach a new frame to point A, which is the orientation of the new link, because there might be a joint at A. And that brings us finally to point B. Oops. Which, once again, might have a different orientation because the end effector might be able to rotate with respect to the previous frame. So drawing in the transforms here, we have theta, which rotates around the x-axis, and a phi, which rotates around the z-axis. So you can maybe easier see what I'm drawing here. And now what this results in is basically we have a rotation around X to get to frame A, and then a rotation in Z to get to frame B. You will potentially be able to, or once you did the exercise, you will see that it's easy to come up with angular velocities between consecutive frames. Because if you look at how the link A rotates with respect to inertia frame, there's only 1 degree of freedom because there's only one joint in between. So we know already that it's rotating around the x-axis. So the only way this rotation velocity can be composed is theta dot 0, 0. So only a rotation around the x is possible. And the rate of this rotation is exactly how quickly our angle theta changes here. Similarly, from A to B, now beware, in A or B frame, we only rotate around the Z axis of A or B, which are identical. The Z direction is identical of both. So here our angular velocity will be 0, 0, phi dot. This is similar to what we had in the previous exercise, where you would figure out what is the displacement across just a single frame or across consecutive frames. Here, let's think about how do frames rotate with respect to each other. And because we always introduce a new frame when there's a new link, or a new joint, it will always be just a vector with one single component not equal to 0, and that component will be the derivative of this joint angle. All right, so composition for angular velocities is pretty easy. So if you want to find out now, how does our final frame B rotate with respect to frame I, then we can simply add them together like so. So we have the rotation from I to A and the rotation from A to B, or let's say differently, how A rotates with respect to I plus how B rotates with respect to A. And you can express this in any frame you like. So usually it makes sense, let me write this here, works in any frame. Usually what we want to do is we want to write IB in I frame, and that means we have this one I frame plus we need the omega AB in I frame as well. So to get to that, we have omega AB in I frame is simply rotation matrix of this times this vector here. So that for the rotation entire angular velocity of frame B with respect to I is as simple as adding the individual rotation velocities or angular velocities together and rotating them all into the correct frame, so you can do the plus operation. For the linear velocity, we have to use this formula down here. So the little long complicated formula that always includes two contributions. One, how does the vector change by itself? And two, how does the frame in which we express this the position vector rotate? So which is basically this angular part that you have a lever arm and an angular rate. How does it move at the end of your lever? So let me derive it here step by step. We have d by dt of r IB, all expressed in I frame, which we can now write as RIB is RIA plus RAB, right? And still all of this expressed in I frame. Because this is a plus, like an addition operation, we can pull them apart. So we have d by dt RIA in I frame plus d by dt RAB in I frame. And what I would recommend, and this is of course a matter of how you want to code it, but what I would recommend is represent this in the I frame and represent this in frame A. That makes it easiest to bring it all together, because then what happens is that we have the first one the direct derivative of RIA in I, and there's no omega term for this one, so I can write it here according to this formula, omega I of I in I cross R.
We just need to find the initial, exactly, final one, and so that, okay, that's the angle that needs to be changed, and this is
IA in I, and of course that will be 0. So because we've expressed it in the I frame, this is clearly 0. And for the second part,
Yeah, I agree. I agree.
we have
the left part we will leave it.
d by dt of r
Yeah, of course.
AB in A
So just the differential
plus, and now here we of course have the omega part because the A frame is potentially moving, cross R AB in A.
should be enough because
So
for the category that you're dealing
again,
with just one degree of freedom, you just need to
this
know
term
what the
here is
maximum
usually
percentage changes.
0 because the point, the displacement between A and B does not change over time, usually because they are fixed. There's just a fixed link length. There's nothing time dependent. So the only contribution that you have from the second vector, the second part of our addition, is how how the AB beam is rotated with omega A. And this is what the last part here is. And as you look above, we already have calculated this term. We know this term from our kinematics. We know that term from our kinematics. And the first term is also usually 0. So this is all you need to code up your linear velocity for point B across the entire chain. I hope that makes it clear. To extend this to multiple chains, of course, all you would have to do is in this formula here, instead of just decomposing it into 2 parts, you would decompose it into multiple parts. So we have RIA and AB and BC and CD, for example. But the principle that every of those components has those 2 contributions, one from the direct time derivative, like this one here, and one from the angular velocity of the frame, this one here, is always the same. And for almost all cases, the first part will be 0 because your link lengths don't change over time. All right, that's it. Good luck with the exercise.